So this is the next section of this week, controllability, where we would be starting with the controllable systems. And these three main topics we would cover in this subsection. First is the metric test, second is the eigenvector test, and third is the Lyapunov test. So far we have discussed mainly about the subspaces and their characterization. Now we will be discussing more about their applications to systems and see that how we can determine whether the system is controllable or not. So first is the metrics test. The continuous and discrete time LTP systems can be represented by these pairs A of t and B of t. So it should be implicitly clear whenever we are discussing about the continuous time systems or the discrete time systems, and most of the time we would be using the slash if we are giving the parallel results for the continuous time and the discrete time. Okay, but the matrices would remain the same, and also the denotation of the time operator. So talking about the reachable systems, so given 2 times t1 greater than t0, the system, now we are formalizing all those subspaces in terms of the systems. The system, or simply the pair AB, is completely state reachable on this time interval t0 to t1 whenever the origin can be transferred to every state. So note this point, every state. We will make use of this in our later results. The controllable systems, the pair is controllable on this time, or completely state controllable on this interval t0 to t1 whenever every state can be transferred to the origin. Okay. So the first result says that the following two statements are equivalent. The n-dimensional pair A and B in time for the time varying case is controllable at time t0. There exists a finite time t1 greater than t0 such that the n cross n matrix WC given by this, which is basically the controllability Gramian, is non-singular. Okay, so if you recall that when we had introduced about the controllability Gramian, when we were discussing about the subspaces, we make an assumption that the controllability Gramian is symmetric and positive semi-definite. When a matrix is positive semi-definite, then it is a singular matrix. Now it gives us a strong result that controllability Gramian, if that Gramian is non-singular or positive definite, then the system would definitely be controllable. Okay. So since this is one of the important results, we'll go through a proof of this, and while going through the proof, we will explore other minor results which might be helpful also. So first we'll see the proof of this 2 implies 4, that is to say, if this controllability Gramian matrix or this n cross n matrix is non-singular, then the system is controllable. So this information is given to us that this matrix is already a non-singular matrix. The response of this ABLTV at time t1 is given as this by the variation of constants formula. So we claim that the input, so recall that this input is nothing but quite similar to the input we had specified while discussing about the characterization of the controllability subspace with the controllability Gramian. So we claim that this input, where eta is specifically given by this now. If you recall, when we had specified this u, we had taken some arbitrary vector eta. Now here we have specified eta to be this one, meaning to say that, so first recall that the controllability says starting from x0 we want to reach to some finite or some x1 value. Okay. Now this result is a bit broader in the sense that we want to transfer x0 at time t0 to x1 at time t1, right? So here either of it could be 0, because we have already seen that in the continuous time case both these definition, reachability and the controllability, coincides. Okay, so we claim that this input can transfer this from x0 to x1, where eta is given by specifically this one. So now what we'll do, we'll apply this u here on the right hand side, and then we will show whether the value of x at t1 is basically coming equal to x1. Okay, so applying this value, it would be this one, since eta is a constant vector. It is not a function of time, it is a function of the specific time. So all these entries in this eta would have a definite value. So that's why I can take this eta outside this integral, which I am integrating over tau. Okay, so now see some similarity. This part, this whole part is nothing but your WC T0 comma T1, and eta is given by this one. So we would have, this part would come as it is. This is, we have WC T0 comma T1. This is the inverse of the controllability Gramian, which comes from the eta, and phi and x0 minus x1. So now this part and this part would become an identity. Phi t1 comma t0 x1 x0 would cancel out from here, this part, and the rest part remains negative of negative x1, meaning to say that x at t1 is basically equal to x1. Now the point of having that assumption that the controllability Gramian is a non-singular matrix, because if it is not, then I could not express eta as like this, because in that case the inverse of WC does not exist. Okay, so this is the proof of the part that if this matrix is non-singular, then the system is controllable, and the controllability of the system ensures that starting from some point x0 at time t0, I could reach to x1 at time t1. Okay, is equal to x1. So now for doing the proof of the 1 implies 2, meaning to say that if it is given that the system is controllable, then it implies that the matrix WC is non-singular. As we have seen earlier, we could also show that if the system is not controllable, then it implies that the matrix WC would be singular, right? So we will prove this by contradiction. So suppose WC T0 comma T1 is singular or positive semi-definite for all T1 greater than T0, right? What does it mean? That there exists a non-zero vector V such that V transpose WC into V is equal to 0. This is nothing but the quadratic form we had studied in the week of stability. Okay, because if this matrix is positive semi-definite, then there exists some non-zero vectors. V is not necessarily 0, but still it could, the quadratic form could be 0. Okay, or I could write this as norm V square with a weighted matrix WC T0 comma T1 equals 0. Okay, WC is basically the weight. Now if I put WC from the result here, I would have this entire part is basically WC, and I can take this constant vectors V inside the integral. Okay, now see some similarity, that again I could write this as a norm which is given by this one, the norm of B transpose, phi transpose and V, the squared norm and this integral. Okay, this is the property of using equivalence between the quadratic form and the norm itself. Now using the one of the property of the norm, that if it is equal to 0, it will only be equal to 0 if this the matrix or the vector inside the norm itself is 0. Okay, which implies this is 0, or I could take the transpose of this part and conclude this one. So I would have B transpose phi into B equal to 0. Okay, for all time tau lying inside the integral t0 comma t1. Now, so suppose if the system is controllable, then there exists an input that transfers the initial state x0, which is specified here, at t0 to xt1 equal to 0. So the idea here is we had given that the matrix is a singular matrix. Okay, now we came to one result. Now we want to prove this by contradiction, saying that if the system would have been controllable, meaning to say that given any initial state which is specified here in the terms of the state transition matrix and the non-zero vector. So we know already that this phi is not 0, this v is not 0. So we are not actually starting from 0, because it might be also possible that starting from x0 is equal to 0, we are reaching to x at t1 is equal to 0, and this is what we had seen in one of the examples, that starting at some 0 initial conditions, if the value of the state at some other time t1 is also equal to 0, then it might be possible that the input does not have any influence over it. So first of all, we need to ensure that this x0 should be non-zero. Okay, so if the system is controllable and there exists an input which could transfer from x0 to x of t1 equal to 0, then the solution of the state equations is given by this one. So x of t1 is equal to 0. This part phi t1 comma t0 is the state transition matrix. This part is the my initial condition x0 plus the rest of the part. Okay, and this part, by using the property of the state transition matrix we had studied in the first week, that the multiplication of state transition matrix t1 comma t0 and t0 comma t1 is basically equal to identity matrix. Okay, so I would have, so from here what we would have this part v plus the rest of the part. Now if I pre-multiply that equation by v transpose, I would have v transpose v plus v transpose the rest of the part. Okay, now this part v transpose v is nothing but equal to the norm square, plus this one is already 0 from the above. So I would have the square of the norm is equal to 0, and this is only possible if the vector itself is 0, and from the beginning we had assumed that it is a non-zero vector. So this was the contradiction, which means that if the system, or sorry, if the controllability Gramian matrix is singular, then it implies that the system is also not controllable. Okay, so this completes the overall proof. So moving forward in this direction, so we had seen that for computing the controllability Gramian, we need the knowledge of the state transition matrix, which may not be available. In fact, we had seen in the first week that there are certain restrictions in computing the state transition matrix, and only for specific structure of the A matrix sometimes it is possible, but for a generic A matrix it might not be possible to compute the state transition matrix. Now if it is not possible to compute the state transition matrix, you cannot compute the controllability Gramian, right? So we need to find some other conditions such that we could escape the computation of the state transition matrix. Okay, so to do this, we require some additional conditions on the matrices A and B. What we require, that we had already assumed that the A B matrices are continuous first of all, but now an additional condition we require that these two matrices to be n minus 1 times continuously differentiable. Okay, so in order to relax the computation of the state transition matrix, we need some additional condition on the AB matrices to be n minus 1 times continuously differentiable. Now before looking at that result, we'll do some bookkeeping so that we have a clear proof by construction itself. So here we define two matrices. One is the M naught, which is given by the B of t itself, and another using the recursions M naught, or starting from M1 to Mn minus 1. So we compute n matrices basically starting from 0 to n minus 1, and using this equation minus A into mm plus the derivative of mm. Okay, and using these two equations we would going to state the result which does not require the computation of the state transition matrix. So let's say, so if I write phi t2 comma t for any fixed t2 and multiply it with the B matrix, it is nothing but equivalent to this. Here I just replace Bt by M naught, which was the in the definition initially. Okay. Now I use this result that the derivative of the state transition matrix is equal to the negative of the state transition matrix into A of t. Now recall from the first week, the original result says that if I take the derivative of the state transition matrix, then it is equal to A of t into the state transition matrix, because this is in fact one of the property of the state transition matrix, that it should satisfy the homogeneous equation for the time varying case. But this standard property is different from this one. So I suggest that you take this as an exercise and show this, that the property of the derivative of the state transition matrix is this one. Starting from here, come to this part, that this is now becomes a fact. Okay, which you can prove by yourself. Okay, so now we compute the derivative of this term which was given on the left hand side. So the derivative, by using the chain rule, we have the derivative of the first into bt plus the first term into the derivative of the second term. Now here, this part I would replace by this one. So it would give me minus phi t2 comma t into at here multiplied by bt, and bt is nothing but my m naught. So using this above, I substitute all those in this equation and finally write this simplified one, where I have taken the state transition matrix common out of this standard term. Okay, now notice here that this term, this whole term is nothing but your m1. If I put m is equal to 0 into this equation, I would have m1 is equal to minus at m naught plus d by dt of m naught. So this becomes nothing but equal to phi, sorry, it should be, you should read this as t2, phi t2 comma t into m1t. Okay, now keep taking the derivatives. So proceeding forward, I takes the m times derivatives of the left hand side, and finally I would see that this part is nothing but every time is equal to the multiplication of the state transition matrix for any fixed time t2 multiplied by this mm which we have defined here by using recursion. Okay.